Alright, welcome back to look at the wheel and axle simple machine problems. Before we jump into these problems, we're going to jump back to our formula page where we're listing our formulas. This first question though, note that it asked what's the linear distance traveled in one revolution of a wheel. Well, the distance of a wheel, what they're asking about, the distance around that outside, is kind of our next formula. And so we'll list that here. And that is the circumference formula. So C stands for circumference, and the formula is that it's pi times diameter. Or it can be written as 2 times pi times r, the radius. And so we'll make a note that is circumference. Alright, so why do we need to know that? Well, in a wheel and axle system, alright, when you're calculating the ideal mechanical advantage, if we're wanting to compare distances, the distance that the effort traveled compared to the distance that the resistance travels is really what we are looking at. And that's really kind of true of the lever too. This will come back. Let me kind of just use this space right here as some scrap area. So imagine we've got a wheel and an axle. Okay, so say we have an operator, so someone that's going to use their hand. Forgive my chicken scratch, but they're going to use their hand to provide effort, and in space they're going to grab onto a point of the wheel, and then they're going to operate the wheel. They're going to rotate it, and as they rotate it, their hand travels in this circular motion. So the distance that their hand traveled through space is what we really want to measure in terms of measuring the distances. Okay, now the distance that the resistance, this axle has resistance, it's going to rotate one circle here at the same time, and so that would be the distance that the resistance traveled. And so it's the difference of these two distances that gives us the ability to make a ratio and kind of demonstrate mechanical advantage. Okay, well, here's kind of the shortcut that goes back to really the lever problems for us. If a circumference is 2 times pi times the radius, and that's true for both of them, right? They just, what would be different is that they have different radiuses. So whichever circle is the effort and resistance really doesn't matter right now. But the idea is that these two distances are both circles, and those distances being circular distances, both are calculated using 2 pi and a radius. Well, since you're going to make a ratio with those, the 2 is a common factor that cancels out, the pi is a common factor that cancels out, and in the end, it's really just the ratio of the radii that makes sense to use to kind of compare these distances. And so when you think of our lever problems, right, think of a lever, two different forces. The effort, I know we've annotated and kind of represented the distance from the fulcrum, right? Well, that really was just the radius. Okay, the operator actually had to move along an arc path, and it's that distance that really would be getting compared to the distance that the resistance would move, and that's also following the path of a circle or an arc. Okay, but it's because of this principle that the 2's and the pi's cancel out, are common factors, that we've decided, you know what, it's easier, kind of simple for us, just to compare these radii. Alright, so I'm going to make that note, and I want to add to our formula the ability to calculate a circumference. Okay, so hope that helps you guys out. Alright, so number 10. It says, what is the linear distance traveled in one revolution of a 36-inch diameter wheel? So that is simply going to be pi times the diameter, which in this case is pi times 36, or 36 pi. Now pi is an irrational decimal. It's never-ending, non-repeating. I'm okay with leaving it in terms of pi. Some teachers might want you to, they might want you to round to a certain place value. You could do that. You could use 3.14 to approximate pi, right? In which case we would do 36 times 3.14. It's common, right? 113.04, and I think that was a 36 inch, correct? Yeah, so our units here will be, still it's just a length, inches. There you go, that's it. Number 11. An industrial water shutoff valve is designed to operate with 30 pounds of effort force. The valve will encounter 200 pounds of resistance. Alright, so I'm going to draw an orthographic view of this being my wheel, and then a concentric circle being the axle. So we've got this wheel, and somebody who's going to operate it, the force would be drawn such that it's tangent to the circle. So this wheel and axle system is designed to operate with 30 pounds of effort force. Right? The axle doesn't want to just spin freely, so there's resistance. There's a resistance force in the opposite direction, and it would be a bigger force. When you're drawing things, if you draw a bigger arrow, it helps to represent a larger force. So FR would be 200 pounds. And then, just to annotate, they've told us that I believe it's the diameter. I'll double check that. What's the diameter? Yep, was 1.5 inch diameter axle. Okay, so there's our picture. Number 11 asks us to sketch and annotate, which is what we just did. Number 12 asks what is the required actual mechanical advantage of the system. So number 12 is going to follow up with the same picture, and AMA, the actual mechanical advantage, is found using the ratio of the forces. So the actual forces help to account for friction and other things that are in the problem, and had we used only distances, we would be ignoring those things. So the resistance force was 200 pounds, the effort force was 30. Okay, I can at least reduce here by dividing both top and bottom by 10, and we're going to end up with an AMA of 6.6 repeating, or I'll just round to 6.67. Again, there are no units on mechanical advantage because our units were the same in that ratio. We had pounds over pounds. Okay, right? 200 pounds, 30 pounds, and the pounds are like a factor that cancel out. Number 13. They asked, what is the required wheel diameter to overcome the resistance force? Okay, we'll go back to our levers and remember the idea of static equilibrium. When was this balanced? We're going to use the same principle. What happens though is the value we get when we solve using static equilibrium would be the diameter of the wheel needed to be in balance, and we're going to want the wheel to be a little bit bigger to give us more leverage so that we can actually overcome this 200 pounds of resistance force. So on the effort side of the problem, we have our 30 pounds times, we can use actually here, it doesn't have to be a radius, we can use, remember it could be, as long as we're comparing apples to apples, let me just write DE for right now, and then over here I'll put 200 for the FR, and then I'll do DR just for now. So we have our forces, right? As long as we compare apples to apples, okay, these distances can be both circumferences, they can be both diameters, or they can be both radii, as long as they're the same. So what they asked for was what is the required wheel diameter? So if what we're trying to find is the wheel diameter, and we already know the other diameter, it makes sense just to keep these as diameters. Okay, so the diameter for the effort is the unknown. The diameter of the axle was the 1.5. Hopefully that makes sense though. I'm using both diameters, diameter in, diameter out. Okay, so I get 30 DE is equal to 1.5 times 200 is 300. We're going to divide both sides of this equation by 30. And that'll give us the effort distance, in this case the diameter, to be 10. Now again, that came from a formula that said we were in static equilibrium. So that means our wheel and axle system would be balanced, but we want to overcome, so we need DE, or the diameter of the wheel, to be greater than 10 inches. That's it, greater than 10. The problem really didn't ask to give a diameter to the nearest whole inch. You know, if they had given maybe so down here some other constraints, maybe they would force us to round up to 11 inches or something like that. But for here, we're good just to say it's simply greater than 10. That was the last problem, right? Yep. All right, the next video we'll discuss pulleys.